Howdy. Let's look at section 3 of chapter 6. This is in the random variable chapter, but it's unit on binomial and geometric random variables, two specific kinds of random variables that are similar but have a key difference that means their work is going to be different and their solutions or applications will be different as well. So in this unit, we will talk about whether binomial conditions are met or geometric conditions are met. Perhaps one or the other, certainly not both, sometimes neither. We'll compute and interpret probabilities for binomial distributions as well as geometric distributions. We'll calculate the mean and the standard deviation of that random variable and interpret those things in context. And finally, we can talk about a normal distribution to approximate the binomial distribution. So what does all that mean? Well, a binomial setting, a binomial variable, is when the same chance process repeats several times, and all we're interested in is whether we have a particular outcome or not. Frequently, that outcome is called a success, and a binomial random variable will count how many times that success happened. So more formally, in this green box here, it says a binomial setting arises when we perform several independent trials of the same chance process, and we record the number of times a particular outcome occurs. We have four conditions, cleverly with an acronym, BINS, BINS for binomial. First of all, we need it to be binary. In other words, each trial can be classified as either a success or a failure. So we don't want to say necessarily that you're having a boy or a girl, or you're flipping heads or tails, or that you're winning or losing, but we'll call the outcome we're looking for a success, and the other outcome is a failure. Note, a success doesn't have to be a good thing. A success could be, for example, a positive outcome on a COVID test, and that's a success. The failure would be that negative outcome if I'm looking to count how many successes or how many positive tests I have. Each trial has to be independent of the others. In other words, knowing the outcome for one trial doesn't tell me anything about the next one. We have a fixed number of times that we're going to do this, and the probability of success is the same each time I do it. So for example, if I flip a coin, I could call it a success if I get heads. Otherwise, it's a failure. Each coin flip is independent. I'm going to count how many heads I get out of 10 trials, and every time I flip the coin, I have the same probability of getting heads. That little acronym can help you remember the conditions for a binomial distribution. So this is a head tossing or coin tossing example. Heads is a success. The probability of getting heads is 0.5 each time we do it, and that's called a binomial random variable when X is the number of times I flip heads. The distribution of that will be called a binomial distribution. You can see here that we look at two parameters, N and P, N being the number of times I try, P being the probability of success. So in a binomial setting, we'll define X as the number of successes. Look at this example. Each child of a particular pair of parents has a 25% chance of having type O blood. Genetics says that children receive genes from their parents independently. So if these parents have 5 children, X will be the number of type O blood children they have, with N is 5 children, and an independent probability, a fixed probability of 0.25 each time. What's the probability? X equals 2. Well, here's what we've got. If the first 2 kids had type O and the other 3 did not, then there's a 25% chance for the first 2 kids and a 75% chance for the next 3 kids, which could be written more succinctly like this. Multiplied out gives you this number. But it might not be the first 2 kids that have type O blood. It might be a different 2 kids. In fact, I see that there are 10 different ways to arrange these 2 successes in here. So if this is the first two kids succeed and the other three fail, I need to multiply that by 10 so that I get all these different orders right here. This tells me there's a 26% chance that if a couple has 5 kids and each kid has a 25% chance of having type O blood, there's a 26% chance that exactly 2 of those kids will have type O blood. Note, in the previous example, any particular arrangement of 2 successes and 3 failures has the same probability. In other words, each of these 10 cases has the same probability because all we're doing is rearranging the 0.25 and the 0.75 in that formula. It'll multiply out to be the same thing. So the trick is, if I try something n number of times and I want k successes, how many different ways can I write it? In this case, if I have 5 tries, 5 kids, with 2 successes, how many different ways can I arrange the 2 successes? This one was 10. How could I generalize it? Well, you can generalize it using what we call the binomial coefficient. So this is called n choose k, n choose k. And n is the number of tries, in this case it was 5, and k is the number of successes. So it's 5 factorial over 2 factorial times 5 minus 2 factorial. Now remember, factorial is just the number times the number minus 1 times the number minus 2 all the way down until I get to 1. And 0 factorial is defined as being 1. So this formula then is the general formula for the binomial distribution. This is the binomial coefficient. N attempts, k successes. The probability of success to the kth power, because that's how many successes I had. And 1 minus p is the probability of failure to the n minus k power, because this is the number of failures that I have. In this example, I had 2 successes and 3 failures. So this was 2, and this was 5 minus 2. So how do I find binomial probabilities? First, state the distribution and the values of interest. Specify a binomial distribution with n number of trials, a probability p of success, and make sure those values are clearly identified. Now, we can also use these functions on the calculator, and I'll show you that in just a second. But first, we're talking about the formula to find the desired probability, and then answer the question back in context. So each child of a particular pair of parents has a 25% chance of type O. Suppose the parents have 5 children. Find the probability exactly 3 of them have type O blood. In this case, X is going to be the number of kids with type O blood. It's binomial with N5 and P 0.25. So here's the formula. The probability X is 3 is 5 choose 3, 5 attempts, 3 successes. The probability of success, and there are 3 of those. The probability of failure, 2 of those, and work that out right here. Should the parents be surprised if, and I'll show you the calculator in just a second, how to use those functions. Should the parents be surprised if more than 3 of their children have type O blood? In other words, what's the probability that more than 3 of them have type O blood? Well, more than 3 means it's either 4 or 5. So here's the formula for 4. Here's the formula for 5. Worked it out. Should they be surprised if more than 3 of them have it? Kind of, because there's only a 1.5% chance that that will happen. Now let me show you how to do this on your calculator. Your version of your TI may be slightly different, but it'll basically be the same thing. So I'm going to press second distributions, and that's this button right here. and then go down or go up, either way, to Binomial PDF. This is a particular value in the binomial distribution. This C is the cumulative value. I'll show you that one in a second. So the particular value means that particularly in this case equaled 3. The number of trials was 5. The probability of success was 0.25. And I had 3 successes. Chicka chicka whir whir. 0.08789, 0.08789. Now you're still going to have to understand how to put the numbers into the formula, but you can always use your calculator to actually do the work. Now with the CDF function, the CDF function is a little bit different, and the way I remember it is, let me get a notebook here. The way I remember it is that the C kind of looks like a less than sign, and so the binomial CDF function always finds the area less than or equal to. So now I'm talking about the binomial CDF, and I always underline that C, and now it kind of looks like this symbol, because that's what the binomial CDF does. So if I wanted to find, for example, the probability that X was less than or equal to 3, I could use the binomial CDF of N, P, X. So if I did this in my calculator, this is the binomial CDF of 5.253, and I get 0.984375. Now you may recall that the problem we just had said, what's the probability X is more than 3? Well, those two symbols don't look the same. You have to do it as less than or equal to. So I'm going to flip this around to 1 minus the probability it's less than or equal to 3. See, the things over here are bigger than 3. So this means what's not less than or equal to 3. Those things are equivalent. So now it's 1 minus 0.984375. So 1 minus that answer. .015625, and that might look like that. So there's how you do those same functions on your calculator. All right, we could describe the probability distribution of a random variable just like any other one by looking at center, shape, spread, cussing the data. So here's what I did. I said, hey, family with 5 kids whose each kid has a 25% chance of having type O blood, how many kids in your family have type O blood? And if I asked lots and lots and lots of them, here's what it would look like. Or perhaps I could use those formulas to figure out these values right here. So it's a right skewed histogram. Center's down in here. Obviously it goes from 0 to 5, but most of them are 0, 1, or 2. Now to find the mean, we're going to take each of these numbers like we've done before, multiply them together, add them up, and I get 1.25. That's the center for this particular problem. The variance, just like we did before, looks like this, like we did in the previous section, where you take each number minus the 1.25 squared times its probability of occurring. This is the variance. I could square root that to get the standard deviation. As always, if you want to go back and try these numbers on your own, just pause the video and give it a go. Now we can make this a little more succinct, a little bit simpler, because we have a binomial distribution, a particular type of distribution, a unique one. And in this case, we can use these formulas to work this problem out. Note, these only work for binomial distributions. So in this example, I had 5 kids with a 25% chance of each kid having type O. 5 times 0.25 is 1.25. Works out a little bit quicker that way. So let's look at this example right here. Now I want to show you, as I thought about it, these formulas again with that problem we just did. So we've got NP, that's 5 and 0.25. This is going to be the mean. I'll go back and show you what we got in just a second. Now to find the standard deviation, it's going to be the square root of n times p times x. Sorry, times q. N times p times q, or n times p times 1 minus p. There's the standard deviation. Go back and look at this slide, one back. Right there at 968, there it is, the standard deviation, the mean 1.25. So these new formulas are much simpler to use than these long formulas, although the long formulas work because it is a distribution. So it is a random variable distribution. These formulas still work. This is just a bit clearer and cleaner. So let's look at this problem now. We've got 21 students who can't tell the difference between tap water and bottled water, so they're just guessing. Each has a 1/3 chance of guessing correctly. X is the number of students who identify correctly which cup is different. So we've got 21 students, probability is 1/3. If each student is independent of the others, then it's a binomial random variable. And so I can use these formulas. NP, on average 7 students will get this correct if Mr. Bullard does this in multiple groups of 21 students. And the standard deviation is 2.16. So if we repeat this lots of times with 21 students, the number getting it right would be different from 7 by an average of 2.16. Binomial distributions are important when we wish to make inferences about the proportion of successes in a population. Almost all real-world sampling is done without replacement, which violates independence because when I pull something out of the pot, the probabilities of getting the next things change. However, if the population is really big, then it doesn't change by enough for me to care. So it says here more technically, when the population is much larger than the sample, a count of successes with an SRS of size n is basically the binomial distribution, with n equal to the sample size and p equal to the proportion of the population, proportion of successes. This is what we call the 10% rule. Basically, I can use the binomial distribution as long as I've sampled less than 10% of the population. My sample size, little n, needs to be less than or equal to 1/10 of the population size, which is big N. Now, if I'm trying to take a sample of, say, Americans, there's no way I'm going to take 10%. I'm good to go to use the binomial distribution. Now, if n gets bigger, that binomial distribution becomes more and more normal looking. So if we have a binomial distribution with a large sample size, we end up with an approximately normal distribution with a mean and standard deviation just like we did before. As a general rule of thumb, we can use a normal approximation when n is big enough so that NP is greater than 10 and N1 minus P is greater than 10. What does that mean? NP, that's this NP. NP is the expected number of successes. N times 1 minus P is the expected number of failures. So as long as we're going to see at least 10 successes and 10 failures, my sample size is big enough so I get 10 yeses and 10 nos, the normal approximation is going to be really close to the binomial distribution, and we will use the normal approximation. That was a binomial situation. Now, there's another situation we'll talk about called a geometric situation, and I don't want you to be confused and think everything's binomial or geometric. We know that's not true. Normal is different. Sometimes normal and binomial are similar, but there's lots and lots and lots of different distributions. Binomial and geometric come up frequently enough where we're giving them some specific attention. The geometric setting is essentially like the binomial one, except now instead of doing whatever it is a fixed number of times, I'm doing it until I finally get my first success. So perhaps I'm a kid shooting free throws in my yard. My shots, if we consider them to be independent, I'm going to continue to shoot this shot until one goes in. Or maybe as I get a little older and I get a little better, I could talk about continuing to shoot a shot until one doesn't go in. And now I'm calling a success, missing the basket. So a geometric situation is when I record the number of tries it takes to get one success. Like before, the probability of success has to be the same each time, and each trial needs to be independent. That's probably violated with my basketball example, but you get the idea of what geometric is looking for. Possible values for y, the geometric variable, are 1, 2, 3, etc. I can't have 0 because I'm going until I get my first success. With the binomial distribution, I could have 0 because that would represent 0 successes in however many attempts I made. Like binomial random variables, it's important to distinguish when the geometric rules will apply and when they don't. So here's a game called the Lucky Day game. The variable of interest is the number of guesses it takes to correctly match the lucky day. What is the probability the first student guesses correctly, second student, whatever. So if it's a day of the week, there's a 1/7 chance that the first student guesses correctly. A 6th, all right, this is going to be a little confusing. Let me say this differently. You're going to guess a day. There's a 1/7 chance that the first person to guess it right gets it right. The probability that it takes 2 tries for somebody to get it right means the first student was wrong and the next student was right. This means the first student guessed incorrectly, the second student guessed incorrectly, the third student was the first one to get it right. Now notice on this case, they're unaware of what the other guesses are. So the guesses are independent and the probabilities are 1/7 each time. And you get the idea that we're going to have a bunch of failures and then the very last one's going to be a success. So all but one of them are failures, and then I get a success and stop. In the geometric distribution, you stop when you get the first success. Here's the way a geometric distribution is going to look. It could take a really long time, so this graph will get cut off at some point, just like our table did. We know that they would all add up to 1, but that top row will actually go to infinity, because theoretically it could take infinity minus 1 wrong guesses before I finally got to the right guess. It's heavily right skewed. The mean is 7, which is actually 1 over the probability, 1 over 1/7. Because on average, it would take 7 guesses to get it right. And here's the standard deviation. You'll be given the formula to find that, but it works the same way. Here's the formula for the mean. The mean of this distribution is 1 over the probability of success. Like I said, you'll be given the formula for standard deviation if you need to use it. Mostly you'd know how to interpret it. If we play this lots and lots and lots of times, that's about how far off we are. Pretty good size standard deviation, because sometimes students are getting it right to begin with. Sometimes it takes a lot longer. That's a flyby overview of the binomial and geometric distributions. You should certainly, as always, work some problems out to see how it comes into practice.